All right, so welcome to this review, the finals review for spring 2019. I hope you make good use of this. All right, so first of all, Newton's laws, and especially Newton's second law, where you get force is equal to mass times acceleration. But remember that force there is the net force. So if there are like two forces acting, you have to find the net force. M stands for mass in kilograms, A is acceleration in meter per second squared, and force is in newtons. So that's the net force, like I said. So remember that, that's the net force. So here's an example which you should be able to understand. If the mass is 1 kilogram and the acceleration is 1 meter per second squared, then the force is 1 Newton, for sure, because it's 1 times 1. So you go 1 kilogram times 1 meter per second squared gives you 1 kilogram meter per second squared. That could be a unit of force, you know that? Just put the units together so you get that. But kilogram meter per second squared is Newton, so that's 1 Newton. So friction is the next topic, and there are two types of friction, static friction and kinetic friction. Here we're talking about kinetic friction. Kinetic friction is when there is actual motion, right? That's why it's called kinetic friction. And mu is a constant called the coefficient of friction, and N is the normal force. The normal force means the perpendicular force. So as shown in this diagram, the weight of the object acts vertically down and the normal force acts vertically up, and they are equal to each other. So the normal force is mg. In this case, N is equal to mg. Therefore, in place of the normal force, you can write mg. And that is always true for any horizontal surface. The normal force is the same as the weight, which is mg. Therefore, if mu is given as 0.40 and mass is 100 kilograms, can we find the friction? Can we find the friction force? Mu times mg, 0.40 times the mass is 100, g is 9.8. With that, calculate, you get friction. So you also know that friction always opposes motion. You know that, right? So when you make the free body diagram, you are going to say if the object is moving to the west, then friction is going to be to the east. So remember that always. Friction is always opposite to the applied force. So here is the next one. I'm bringing in Newton's law and friction and giving you this example. So you have a 10 kilogram object and there are two forces acting on it, 65 newtons in one direction and 20 newtons in the opposite direction. And this 20 newtons may be friction, could be friction. And so first you have to find the net force. And you also know that the weight, mg, and normal force are opposite to each other. So that's the free body diagram. Remember free body diagrams? Yeah. On a horizontal surface, and then depending on what I'm trying to tell you, okay, if I give you the mass as 10 kilograms, obviously the weight is 98 newtons, 10 times 9.8. And in this case, the normal force is exactly the same as weight, because it's on a horizontal surface. And then I'm asking you to find mu. So I'll give you a minute to go calculate mu. So here to find mu, what you're going to do is use F is equal to mu times N. Friction is 20. You find the net force. Net force is equal to mass times acceleration. And net force is 65 minus 20. You get 45 newtons. That's the net force, and then put it into the equation mass times acceleration and calculate the acceleration. There you go. 45 by 10, 4.5 meter per second squared is the acceleration. So again, when you find mu, you don't need the net force, you only need friction. But when you calculate the acceleration, you need the net force. Linear momentum. Linear momentum is the product of mass and velocity, right? It's a vector, and the direction of momentum is the same as the direction of velocity. So linear momentum is a vector, m is mass in kilograms, velocity in meter per second, so the unit of momentum is kilogram meter per second. Impulse. Impulse has two formulas. One is impulse is the product of average force and the time for which it acts. And the second formula for impulse is it is the change in momentum. So you have two formulas for impulse, both of which you can put equal to each other. And here is a question. Mass is taken as 1 kilogram, and this object is moving at 10 meters per second. And then you apply a force in the same direction, and therefore the velocity increases to 15 meters per second. Right? 15 meters per second there. And you're asked to find the time for which it acts. So what you do is you find the initial momentum, which is mass times velocity. So 1 times 10 is the initial momentum. And then you find the final momentum, which is 1 times 15. That's the final momentum, isn't it? You all can talk. There's no problem. It's like you stop breathing. Okay. So now find the change in momentum. 15 minus 10, 5 kilogram meter per second is the change in momentum. So if I give you the force, then you can find the time. Can't you? Yeah. If I give you the force, then you can find the time using those two equations. Let's go 100 times. That time should be 5, and then you get the time as 0.05 seconds. So I think I'm giving you another example, which means this is right there on the exam. That's what it means if I'm spending more time. So here I'm going with, well, the mass is 1 kilogram. The object is moving at 12 meters per second in one direction. And watch this. This time the force is applied opposite to its motion, isn't it? So the object is trying to go to the east and the force is applied to the west. And then after the force is applied, it's moving at 13 meters per second. So if I ask you what's the change in velocity, I hope you're not going to say 1 meter per second. Are you going to change and say 1 meter per second? No. It was going at 12 in one direction. Now it's going at 13 in the opposite direction, isn't it? So be careful with that. So let's see how I built that question. All right, again, it's find the time of contact of the force. So this time I've given you, so I think I'm doing it exactly the same way as before. Find the initial momentum, which is 1 times 12, but look at that. When I find the final momentum, why do I have a negative? Because the 13 is in the opposite direction. So that's what you got to remember. So it's negative 13. Therefore, when I take the change is always final minus initial. But in this case, it doesn't matter. The number is going to come up as 25. One way you get it as negative 25, right? The other way you get it as positive 25. The change is, the magnitude of the change is 25. That's all that matters. And then put the two formulas together like we did before. 100 times the time is the change, which is 25, and do that math. So now you understand that to create that big a change, the force had to act for a longer time, see? In the last case, I think we got 0.05 seconds, didn't we? And this time it's 5 times more. So that's why it's moving in the opposite direction. There are 2 types of collisions, elastic and inelastic collision. Right? What's the difference between them? In an elastic collision, kinetic energy is conserved. In an inelastic collision, kinetic energy is not conserved. Like, remember, in both of them, momentum is conserved, right? Momentum is always conserved. But in an elastic, kinetic energy is conserved on top of momentum. So I'm trying to say momentum is always conserved in both. So here's an example. And in this example, you have 2 masses, 1 kilogram and 0.5, moving at those velocities, 2 meters per second and 1 meter per second. And then after collision, they stick together. See? So can you tell me, is this elastic or inelastic? This is perfectly inelastic, right? This is where maximum kinetic energy is lost if 2 objects stick together. And then I'm asking you to find their common velocity, which is easy because you apply the conservation of momentum, correct? Where you go m1 v1 plus m2 v2 is equal to
M1 plus M2.
right? m1 plus m2 times the velocity because they are together. That is what I'm doing. 1 times 2 plus 0.5 times 1 is equal to 1.5 times. Why 1.5? 1 plus 0.5. So I added them up. You have the total mass there, and then you get the final velocity is 1.67 meter per second. So I think I'm asking, is the collision elastic? Surely not. This collision is inelastic, right? And if I ask you to find the loss of kinetic energy, would you be able to do it? The loss of kinetic energy? Yeah. What is the formula for kinetic energy? 1/2 times mass times velocity squared. So you got to find the total before, total after, find the difference. You could do that too. So initial total kinetic energy, I'm using 1/2 times mass times velocity squared. That's the total initial kinetic energy. And then the final kinetic energy, of course, the total. And you get 2.08 joules. So you see that the final is certainly less than the initial. And the difference gives you the loss of kinetic energy. Okay, it is an inelastic collision, right? Now, this is a lab that we did, the ballistic pendulum. Do you all remember? And there is a question on that. Just the ballistic pendulum, if you don't remember, let me remind you. What did we have? We had this heavy pendulum, and then you shot a ball into it, it got stuck in it, and it moved up. Do you all remember that? Okay, so in this case, surely this is an inelastic collision, and we can use this method to find the speed at which this was fired into it. That's what I'm doing. I'm going to show you all the ideas that we use here, chiefly 2. Is momentum conserved here? Yes. Come on. And initially, just when the bullet or the ball gets stuck in it, they both have kinetic energy. But as they move up, that kinetic energy changes into potential energy. So it's energy conservation and momentum conservation, both together. Momentum conservation and energy conservation. So there are the masses. And that's the total mass after they got together. And then, so what is that? That's where I am saying the potential energy, isn't potential energy mgh, is equal to the initial kinetic energy. So what is V final here? What do I mean? It's the final velocity with which they started moving up. That's what I mean. So the kinetic energy is equal to the potential energy. And then I can find an expression for the final velocity as square root 2gh. And then you apply the conservation of momentum. Got to be careful there. Somebody tell me what's the initial momentum of the pendulum? 0. So that's where that 0 comes. And then they are together, so I added their masses. Does that formula equation make sense now? That's the momentum of the bullet. Initial, this is the initial momentum of the pendulum. It's not moving, so it's 0. And then they are together, so I add the mass. Multiply with the velocity with which they begin their motion up. So I think I'm giving numbers now. I'm saying let the height be 10 centimeters. Right? I just assume that the height is 10 centimeters, which makes it 0.1 meter. And then I calculated the final velocity and then plug that final velocity into this equation to find the velocity of the bullet. So do that math and you get the velocity of the ball or the bullet, whatever you want to call it, as 15.4 meter per second. So those are the two that we use here. Conservation of energy here and conservation of momentum. So next topic is static equilibrium, which is again a lab that we did. Remember the meter stick lab that we did? Balancing it out. Static equilibrium, 2 conditions. The torque must be balanced and the forces must be balanced. Now, talking about torque. Torque is RF sine theta. Now, what are those terms? R is the distance, which could be the radius. F is the force, and theta is the angle. So, if the radius or the distance is given, the force is given, and the angle is given, surely you should be able to calculate the torque, which is simple algebra, which would give you 2.5 Newton meter. And I'm trying to explain that by showing you what I mean by the angle. So this is the force. That's where the distance is measured. So this would be the pivot, okay? So you're applying the force there. And that's 30 degrees, that's 10 newtons, and that's the distance. So that should make it very clear. So that's the pivot about which it's rotating. Are you getting maximum effect of this force? Surely the answer is no. To get maximum effect, you would have to apply it at what angle? 90 degrees. So that force of 10 Newton would have to have been this way to get maximum effect, because then you would have got the torque as 10 times 0.5, which would be 5 Newton meter. Did you hear me? Now you only got half the effect. So that's what you got to remember. So if I ask you, how do you get maximum torque? You have to know theta is 90 degrees. And if theta is 0 degrees, of course you don't get any torque. Then it won't turn, will it? So those are the things that you need to know from that topic. So I think I'm giving another example on static equilibrium. All right, this is the lab that we did. So you have the pivot, and it's not a meter stick because you can see that the distances are like 1 meter and 2 meter and all that. So this force of 100 newtons is being applied 2 meters away from the pivot. 50 Newton force is applied 1 meter away from the pivot. 2 forces there, and there is a third force here at 2.5 meter, and I'm asking you to calculate that force. Can you do it? Whenever you work out problems like this, you have to first find out which are the clockwise ones. The ones on the right side are trying to turn it clockwise about the pivot. So 2 clockwise, and there's only 1 counterclockwise, right? And the clockwise torque is 50 times 1 plus 100 times 2. Because in this case, the angle is 90, as you can see. So it's just the product of force and the distance. So F times 2.5, which is the counterclockwise one, should be equal to 50 times 1 plus 100 times 2. And then you do the math. So on the right side, you get 250, and then divide that by 2.5. Obviously, I'm picking good numbers. So 250 by 2.5 is 100 newtons. That's how we do those problems. So, elasticity. Remember Young's modulus? Do you remember that when you apply force on something, it can stretch? Like a rubber band or even steel, all of them stretch. And Young's modulus is stress by strain. Stress is defined as force by area. Strain is change in length by the original length. So here I'm giving an example of, let's say the force is 100 newtons and the area is 0.1 meter squared, which gives you the stress of 1000 Newton per meter squared. And then the strain is, let's say, 1 by 1000, which means if the original length of that was 1000 millimeters, it stretches by 1 millimeter, right? You just have to have consistent units for this. If this is in millimeter, this also has to be in millimeters. So once I give you the stress and the strain, you can find the Young's modulus. So just go 1000 by 1 by 1000, which gives you 10 to the power 6 Newton per meter squared. That is the Young's modulus. And sometimes you will have to calculate the area of cross section from the radius, which is what I'm showing. Now in this case, I gave you the area, right, directly, but I could give you the radius, and A is the area of this part, isn't it? The area of cross section. So if I give you the radius, you got to use A is equal to pi r squared and find the topic here. Any guesses? What is that topic? What is this topic? Fluids. And so in fluids, you have what's called the equation of continuity, where you have liquid flowing through a tube which has different cross sections. Which cross section is going to go faster? The smaller one. And to find that, we use the equation of continuity. So I've given the speed and the area here, and I've given you the area on the other side, and you could find the speed there. Can you? What is the equation of continuity? What is the equation of continuity? Come on. That's it. The product of area and velocity must be equal on both. So that's the equation of continuity. Just consistent units, and you can calculate the speed of flow, which is of course 40 centimeter per second, because the area is 4 times less. The speed is going to be 4 times more. That makes sense? That is the equation of continuity. But also in this case, you could be asked to find the volume flowing out in a second. Does anybody know the formula for volume flowing out? It's actually by time. So it's, whatever you did here, the product gives you the volume flowing out per second. Area times velocity gives you the volume flowing out per second. So the volume flowing per second is simply the product of area and velocity. So you can use either the left side or the right side, because you know they're equal, and I get 1000 centimeter cube per second, which is 1 liter per second, right? That's how you find the volume flowing per second. So remember this formula in connection with this flow of fluids. So pressure exerted by liquids, or rather pressure generally is given by force by area, isn't it? Pressure is force by area, measured in pascals, which is Newton per meter squared. So if there is a 100 kilogram mass applying its weight on an area of that much, what's the pressure? I can't ask a simpler question than that. Because there again, students could make a mistake. Somebody could just go 100 divided by 0.1. Would that be right? See, they're forgetting that this is mass. That's not the force. So to find the force, you would have to calculate its weight, wouldn't you? That's all you got to do. Simple things. So to find the pressure, go mg by A. And its weight divided by the area gives you the pressure in pascals. Topic is Archimedes principle, a topic that you like. This is another lab. Didn't we do this lab where we found the relative density or specific gravity of objects? So anyways, Archimedes principle talks about the buoyant force. You know, the buoyant force is the upward force exerted by a fluid on any solid. And what's that given by? It's given by volume times density times g. So the volume of the fluid displaced times the density of the fluid multiplied by g. So that's actually the weight of fluid displaced, isn't it? The weight of fluid displaced. So here's an example. So this solid is completely submerged. So when I say completely submerged, wouldn't its volume be the same as the volume of liquid displaced? But what if it's only half submerged? Then you only take half of its volume. All right, so in this case, if I give you the volume and the density, that's water, recognize that's the density of water, you can find the buoyant force, 980 newtons. That simple. So coming towards the last few topics, Carnots Engine. What is that? What's Carnots Engine? It's a heat engine which converts heat into work. So it absorbs heat, uses a part of it to do work, and rejects what's remaining. That's it. You got it. Just remember, it absorbs QH. It gives out QC, and the work done is, what's the work done in this case? Like if it takes 1,000 joules and then rejects 700 joules, 300 is missing. So to find the work, you take the difference between QH and QC. And also the temperatures are TH and TC. That's the temperature of the source, and TC is the temperature of the sink. Efficiency is given by two formulas, or maybe three. First of all, efficiency is work over QH, but work is QH minus QC, remember. Or efficiency can be TH minus TC by TH. So there are multiple formulas here. So efficiency is either work over QH. Again, remember work is QH minus QC, right? So similar formulas. T must be in Kelvin. T must be in Kelvin. All right, so here's the example. TH, TC given, find efficiency. Can you do it? Please don't go 127 minus 27 because that's in Celsius. Change both. Again, I'm using good numbers. So this is 400 Kelvin and this is 300. So 400 minus 300 by 400, 0.25 or 25%. If you express it as a percentage, you get it as 25%. Change in entropy. Remember entropy? Entropy is the, it's the measure of disorder of a system and the unavailable energy, all of that stuff, right? But how do you calculate entropy? Change in entropy is, anybody? dq by t. The heat entering divided by the temperature. So ds is dq by t. And dq could be mc delta t. What is that? If you're heating or cooling, isn't that what you use? Mass times, what's the C? Specific heat. What's this? Change in temperature. Or if it's a change in phase, dq would be mass times the latent heat. Now, major mistake, there's no change in temperature there, remember. So two formulas for dq. So I think I'm giving an example here, change in entropy to convert 1 kilogram of ice into water at 0 degrees Celsius. That's a change of phase. So which one of these two would you use? This one? Right? Yep. And then the mass is given, the latent heat will be given, all constants will be given, and T is, look again. You'd never use 0. It will be a disaster if you divide by 0 here, you know. So 273 Kelvin, and then you get change in entropy. The unit of entropy is joule per Kelvin. Thermodynamics. Isn't that what we've been doing? Carnots Engine. First law. Second law. What is the first law? This is the first law. What is that? Explain. Heat entering or leaving is equal to, what is this? Anybody? Change in internal energy plus work done. Okay, so that's the first law of thermodynamics. Second law. What is the second law? Heat spontaneously flows from a hot object to a cold object. Spontaneously, without us doing anything. Naturally. But if you want it to flow from a cold to a hot, you got to do work on it. See? You got to do work on it. Is that clear? Unless you add work, you cannot transfer heat from a cold object to a hot object. So those are the two laws of thermodynamics. Oscillations, we did this today. So here, period of a spring. What is the equation? T is equal to 2 pi root m by k, where k is also called force constant. Remember, it could be spring constant or force constant. Here's an example. 0.1 kilogram, 10 Newton per meter. Find the period. So easy. Just plug it into that equation. 2 pi square root m by k. Do the calculations, you get 0.63 seconds. That's how you find the period of oscillations of a spring. And you could find this frequency, right? It's the reciprocal of that, right? Yeah. Simple pendulum. I think I gave you the formula for a simple pendulum. Time period is 2 pi square root L by G. Right? L is the length, G is 9.8 meter per second squared. Find the period. Here's the example. This one would give you 2 seconds. So if the length is 1 meter, and you plug in the numbers, you're going to get 2 seconds. So if you were using a string as a pendulum, in a clock, you would have had to use this big a string. Then the clock becomes too big, you know. That's why we go in for a metal, which is not a simple pendulum, just saying it's called a compound pendulum because it's not a string. That's why we could get a smaller length. Wave speed. Velocity of a wave is the product of frequency and wavelength. Lambda is wavelength, f is the frequency. that's how you calculate the speed. Frequency is in hertz, wavelength is in meter, and speed is in meter per second. And then wave speed in a stretched wire is root. Please use FT here, can you? FT, please use FT instead of T there, because otherwise you get confused with period. There, again, I'm telling you, that's the tension, right? So use FT. And although you think I've not given you this equation, I have. You will see it soon. Yeah, T is the tension. M is the linear density. Remember I told you, what do you mean by linear density? Mass of 1 meter of the string. All right, now I changed the T to FT so you don't get confused with time period. Okay. That's actually the end. So wish you all the best. We'll see you on Wednesday.